I'm not going to talk about wavelets, I'm sorry, not about machine learning. So I'll tell you why. So the title of the talk is Lippmann Photography, the Art and Science of Multispectral Imagery. So at least it has images in it, actually lots of them. But you know, the true reason I came is to say happy birthday, Stefan. I had the chance, the honor to know him for more than 3 decades, not quite as long as Stefan. Yeah, I didn't go to the glitzy schools. I'm sorry, I'm from Switzerland. So
now it's the reference one.
So,
the other one has disappeared.
So, but Stefan, when I met Stefan, which was the late 80s, I think, in New York, there was a magic group of people that really transformed the way I looked at science and what I was doing. I was sort of came avec les pieds dans la boue as an engineer, and you know, I met Yves Meyer, Ingrid Dopschi, Alex Grossman, Albert Cohen, many people here. Rafi Koifman, Dave, of course, Dave Donahoe, Patrick Flandrin. There were graduate students like Rich and Eero. They made, you know, their career as well. And I have to say, Stefan's influence was major on the way I would actually do things. And you all know it. He came into a field which was sort of things were up in the air, things had been discovered here and there, lots of things were happening, and he came with a very synthetic view and formalized what was, you know, bits and pieces in some sense. At least that's how I knew it before, and that's how I discovered it after meeting Stefan. And for this, I would like to thank you. That was, of course, the start of an incredible trajectory that you all know of Stefan. One that was not mentioned, that he took a sabbatical and made a startup, which is something very, very hard to do, right? And Joa knows about that one. And so I really would like to thank you, Stefan, for your intellectual leadership, but also for your friendship over all these years. Thank you. Thank you, Stefan. Good. So now to the talk. Thank you, Gabriel and Joanne, for organizing a fantastic workshop. For me, it's a holiday, okay, when I come here. Some of you know that at some point in my career, I took a wrong turn. I actually know exactly when and where. And you might have noted, because my slides are in PowerPoint, right? So clearly I'm not a researcher anymore. So the joke is that when you are a professor, you have to deal with numbers, typical irrational numbers. When you start to, you know, the academic management ladder, you become department head, you deal with integers, budgets, right? And by the time you are where I am, you only use the binary system. You only take decisions, right? Mostly wrong, but at least no complex numbers involved. Okay, so when I was invited to come here, I was, you know, I was super nervous, right? What I'm going to talk about, you know, from coming from Switzerland, coming to France, coming to Paris, coming to IHES, of all places. So I got a copy of Grothendieck's Récolte et Sommeil. Okay, that was a start. I haven't read it yet. I wait until I retire or get a sabbatical. I could ask the president of EPFL to give me a sabbatical. That might be a good idea. So in great humility, I come here. I'm not going to tell you about mathematics, but I'm going to tell you about the great French physicist, Gabriel Lippmann. Then I'll use a little bit of great French mathematics from the 19th century, which is Fourier analysis. So I didn't get it to go into wavelets. In that particular case, I don't think it was required. And then we'll come back to physics, right? So it's super interdisciplinary. When I listened to you, Maureen, you had also, you know, this interdisciplinary view. It's something I like. And I also learned actually through the adventure with wavelets, which is indeed a very interdisciplinary topic. Good. So what am I going to talk about? I'm going to talk about this guy here, Gabriel Lippmann. That's a photograph of him taken by his wife using, of course, the Lippmann technique, right? Now, this is, you know, stuff for cocktail parties, right? Don't just take a selfie, right? Take your own new invented photographic method to take your portrait. So I'm going to talk about this Lippmann photography and why I still think it's interesting and potentially important. Oops, sure enough. So I'm not going to put this.
Put it in your pocket.
I'm going to put it here.
And the microphone, you have to.
Yeah, no worries. I knew it shouldn't be at some random place. C'est bon. Okay, so I'm going to explain what Lippmann photography is because most people don't know it. I actually have a Lippmann photograph here, which is very valuable, so please don't run away with it. It's also very difficult to watch. It's part of the problem. And then we'll do the analysis of Lippmann photography. The reason is that it was invented more than 100 years ago, but it wasn't really understood fully, okay? And we don't claim we understand it fully, but we made a few advances on this, so that's part two. And then, of course, once you understand it, you say, we want to change iPhones and have, digital Lippmann photography, so there is a proposal. And then we come back to physics, because the method of Lippmann photography is an extremely powerful storage method, potentially, okay? And given all the TikTok videos, we need to have better storage methods, right? Obviously, long-term storage method. And then I'll talk a little bit about science communication, which is something I spend, of course, some time about. Okay, so as I said, it was invented in the 19th century, but Lippmann invented something else, which is called la photographie intégrale, which is now called, these are the plenoptic function. Roy, you know this. I don't know if you knew that Lippmann had actually invented it. I always thought it was your advisor, Ted Idelson, but Lippmann actually wrote a paper about this early in the 20th century. And so he did two major things just in visual information recording, but he did many other things and got, as I said, the Nobel Prize in 1908. So here are a few examples of Lippmann photographs. Of course, these are totally wrong because it's projected on a standard projector which has only 3 colors, and so it doesn't give justice at all to the method that Lippmann invented. Now, the reason why we studied this was total serendipity, because there happens to be a collection at the local photo museum, and I'll come back to this, of Gabriel Lippmann's plate, and when we discovered them, we decided we wanted to understand how it was done. I have a little movie, I hope it's coming. Okay, so it's very difficult to watch these plates because it's a method of reflection. It's Bragg gratings, essentially sophisticated Bragg gratings. So depending on how you look at it, you see marvelous colors or you don't see anything. Okay, good. Now, it's all about light. In the end, photography is about light. So here is a picture taken by Gilles Baechler, who did a large part of his PhD thesis on Lippmann photography. And in this image, you see the 3 versions of light. One is corpuscular theory, which is essentially ray tracing. So you have reflections, you have wave theory. If you remember, there were bubbles, you have interference that you explain with wave theory. Finally, you have the electromagnetic theory, and for example, here you have polarization on the left side. Polarizing filter has taken out most of the reflections, right? And so when you talk about photography, you always have to think, or computer vision, or image analysis, or whatever. You always have to think, which version of light, or maybe a combination, is actually involved in the phenomenon. Now, interference photography, which is what Lippmann does, was known by the physicists, Bragg gratings, for example. It was used in interferometry, the Michelson interferometer. It was also used to detect black holes, right? The LIGO experiment is essentially an sophisticated, very large-scale Michelson interferometer. Good. Okay, so what was Gabriel Lippmann's idea? The guy had incredible intuition. He said, well, if I have a photographic emulsion that is thick enough, and I can have standing waves of incoming light, okay? So you see red, green, and blue coming in. With a mirror, you will have standing waves, and if I wait long enough, and sometimes it's relatively long, these standing waves will be imprinted in the emulsion, right? And if it's imprinted, and that's where he had an incredible intuition, probably it will reproduce the same colors because there will be a Bragg grating inside the photographic emulsion, right? Now we did these experiments. Let me skip this because it takes too long, but of course it's a very complicated method to do. And shortly after he invented it, Kodachrome invented Kodachrome, and that was the end of Lippmann photography because that was much simpler and much cheaper. Okay, so here are some reasons why it's not the most popular color photographic method. And as I said, depending on how you look at it, it will be very beautiful or it will be a bummer. And that also didn't help the popularity of the thing. So here you see, well, on the left is just a regular photograph, but it shows the interferential methods that you see in rainbows. On the right side, you see how regular photography, that's analog photography, but digital works exactly the same way. Now, Lippmann said something. He said, "La couleur de l'image est la même que celle de l'objet." When you read this, you think, that must be a theorem, right? And then you try to prove the theorem. And it turns out it would be absolutely magical, right? That methods that is very complicated, involves, you know, all sorts of processes. By chance, recording and viewing would be, you know, it would be a unitary operator in some sense. And so when we looked at it, we thought, that sounds like, yeah, that would really be a miracle, okay? And that's really the origin of all the work we did. Now, to do this, we needed to understand Lippmann photography. So we found a photographer from Portugal who does this. There are a handful of people that still do Lippmann photography as a hobby. He came to Lausanne, that's Felipe Alves here in the picture, taught us how to do it so that we could actually produce new Lippmann photographs that we could test, we could put into, you know, X-ray machines and so on to verify the theory we did develop. Okay, so here is an example of a focused ion beam image, and you see in the, so that's a small, it's maybe a few millimeters thick. You see that there is really this grating phenomenon that happens inside the Lippmann photograph, right? Good. Okay, so now we want to see if la couleur de l'image reproduite est la même que l'original. I could have said, you know, that's a theorem that we would like to show. And so we looked at the original papers, which are quite complicated but sophisticated. They are complex, but for some reason Lippmann didn't like complex numbers, so it's quite elaborate to do Fourier analysis without complex numbers. And what is interesting is that people understood the theory for for single frequency waves, right? So pure colors, it was sort of understood what the standing wave would do and so on. For mixed color, people didn't agree among each other, physicists and chemists and so on. And so there was an interesting question to pursue. So we did a model of this, and that's a typical view if you come from signal processing. You have an input spectrum, you have a recording mechanism, so you have an incoming wave, you have a mirror outcoming wave, a standing wave, blah, blah, blah. Okay, then you develop this, that's the second step, right? So you have the emulsion, you go into the lab, you use all sorts of chemicals. That will have a certain effect because it has, you know, a non-trivial thickness, that will do some damping effect. And then the viewing process again has an incoming white light wave coming in, a reflected wave, which will interact with these Bragg gratings, and that will have another effect, right? So the question was, is this input to output the identity operator? And as you can already guess, it is not. And then we should understand, you know, how much of a transformation this will do. Okay, here is a more detailed thing. Again, I'm worried that I will go over time. So you have the plate here with the thickness. The emulsion is much thicker than in regular photography. You have the development process. And finally have the viewing where you have to be careful that the reflection from the white light doesn't blind you. So there is a whole contraption to actually view Lippmann photographs. Good. Okay, then you sit down and you do some elementary Fourier analysis. So you take the wave function that comes in, which is the transformation here of the spectrum with, you know, time and thickness. Then the reflection, what you get out is, the standing wave is the sum of incoming waves, the reflected wave, that gives you this expression. Then the intensity becomes something, it's not very complex, but where you have the power spectrum of the incoming image, which is shaped here by a shaping function, which in the end will essentially convolve the spectrum. Okay. And this can be done easily with a single frequency wave. Then you have this at the output, and you have this filtering function that we'll see a couple of times. which essentially you have a single frequency coming in. This is the standing wave that is being recorded by the Lippmann process and that is shaped by this convolution kernel. Okay. As I said, the multi-frequency case for some reason was not properly analyzed. And so this is done here, and at the end of the day, you see that's a reflected spectrum, that's a frequency at the output, is the incoming spectrum convolved here with this function that comes here from the combined effect of the analysis and synthesis of the Lippmann process. Okay, so the answer is it is not the same color because that's not the trivial kernel. All right, and then you can go through different, examples of this. The reflective medium Lippmann, that's another reason why it wasn't too popular. He used as a reflective medium mercury, right, which, as you know, is highly toxic. You can use air at the interface, will also do the trick. Mercury will put you a node here at the reflected spectrum. Air will not put a node. So this will transform the way colors are actually being reproduced. And we can see this. So in the end, what we wanted to do is always have a theoretical analysis, which is still an approximation. We didn't use quantum electrodynamics theory to do this. It's still the wave equation, which is an approximation. So we always try to understand the analysis of the process, then do a simulation version of it, and then actually compare to actual physical experiments. And that's why this is the longest research project I've ever been involved with, because if you try to do this entire system and essentially derive a digital twin of the physical experiment, it can become quite complicated. Okay, so for example, we gave some explanations which were sort of intuitively understood, that there is a red shift if you use mercury, you have a blue shift if you use an air interface, and so on. Good. You have some other effects that's sort of obvious. These Lippmann plates, the theory was done with infinite plates, which is not very practical. So finite plates will create the Gibbs phenomenon. So the reproduced spectrum here will have lots of ripples. If you do the development in a certain way, it will damp the ripples. And this is certainly something that Lippmann understood. And there was a lot of cooking when you do the development of Lippmann plates. Good. Let me maybe skip this one, it's not so important. And then we wanted to do ground truth experiments. So we did, color charts and, precise measurements with spectrum analyzers. So Lippmann plate, which is a reproduction of this, is not perfect because we were not Lippmann. And then we try to invert the effect of the convolutional kernels that I mentioned earlier, so as to try to reproduce the original colors perfectly. This turns out to be difficult. It's a numerical procedure, constrained least squares with all the boundary conditions we could put in. And as you can see, this is an imperfect experiment. Why were we trying to do this? We wanted to go back to the original Lippmann plates that date from late 19th century. So, for example, this is an image from the Swiss Alps, and one question we are trying to pursue is to know if the color of the sky, in the 19th century, was truly different from the color of the sky we see today. Because it's one of the one of these myth, right, that because of pollution and so on, the blue sky is actually not blue. This is very hard to verify because we don't have access to the exact methods that Lippmann used when he was developing his plates. Nonetheless, we are not very far from, by this reproduction from the originals, which were measured here, and this is our numerical reconstruction. Good. How am I doing on time? I didn't check at all. I'm sorry. 12 minutes? Oh, then I should do okay. Okay. So, given that, I spent a lot of time doing digital signal processing, the question was, can we actually do a digital Lippmann camera? And that's where we started working with, people from physics that know how to do these things. And the idea is relatively obvious. You try to build Michelson interferometer So the classic interferometer has a single source, a laser, and a single detector. It gives you a one-dimensional output. If you generalize this, you have a two-dimensional input. You have this halfway mirror here that creates the interference. And what you do, or what you build, is a movable mirror with a piezoelectric system so that you can essentially record all the layers of a Lippmann plate. The idea is relatively obvious, but not completely easy to implement. But it's, this is not rocket science. That can be done. For some reason, nobody has built multispectral cameras this way. So there might be a good reason, I'm not sure. But that's one way to build a very fine multispectral camera. I forgot to say, the key question, of course, in I don't know why I missed this. It was part of my slides. The question was, how many colors does a Lippmann plate actually record, right? So I was complaining about Kodachrome, which has only 3 colors, 3 color channels like current digital cameras. So Lippmann plates of the size, of the thickness that Gabriel Lippmann was using, record about 24 colors. So it's the first example of a multispectral camera. Of course, now there are many other ways to do multispectral cameras, but this remains one of the methods to have very, very high resolution multispectral cameras. Okay. So this we actually built with students, and so that's a handheld Lippmann camera. It will be soon in an Apple store near you. No, don't worry. It's still a little bit clunky. And of course, the true reason why this is not going to take off, you cannot just build a digital Lippmann camera. You need to build a digital Lippmann display device, right? Because all that stuff we are looking at is trichromatic, so it's not interesting. This is something we also looked at, but then we discovered that Qualcomm had invested, I think, $1 billion in a company that was trying to do displays which was imitating essentially the iridescence of butterfly wings, right? I forget the name of the company, Ivan, you might remember. And this was so difficult to do, so to generate colors which were much, much richer than actually the trichromatry that is currently used in displays, that after $1 billion, even Qualcomm gave up. Okay, so we're not quite there yet. But that's actually one of the grails, I think, in display technologies, to be able to do the dual of Lippmann photography and to have a very cheap, very high multispectral display. All right, so then we said, well, and you can go through the numbers, so a Lippmann plate is an incredibly powerful storage system, and it's also very durable, right? These things are from the 19th century, and they look just perfect. And so we teamed up with Yves Belloir, a physicist at EPFL, who is, does very sophisticated material science using femtosecond lasers. And that's all stuff I had no idea about. And the idea was to say, well, in 3D storage, okay, I mean, our view of storage is two-dimensional, CD, disks, tapes, and so on, or for that matter, permanent storage. So you could have 3 dimensions. You could have, at each location, intensity, rotation, and potentially color. That would give you 6 dimensions, right? That's pretty good. That's 4 more than what we are used to. And so we're not alone of thinking about this. Actually, you can compare, that's a Microsoft project, Project Silica, so the goal is to have very long-term storage, 500 years for the TikTok videos, very important. If you compare what we estimate, but these are very rough numbers, is that Lippmann storage could be an order of magnitude more than these projects that Microsoft is currently running. Okay, so what is the idea behind it? Well, is to do Lippmann plates in a digital way to print them, right? And so you take layers of silica or glass or whatever, and which has a certain reflectance function, which is dependent here on the structure of the layers. And then with a femtosecond laser, which can generate a lot of energy in a collimated spot, you actually do a transformation of the material. Okay, so far so good, and this can be done, and you modify a piece of the era, and then serendipity again. the PhD student who was doing this made an error when he created the layers. Instead of having regular layers, we come back maybe to Fourier, he had printed irregular layers of this sandwich, and he discovered that actually the transformation was bound in a single layer. Okay, and of course, this is of course very important, because if you want higher density, you want higher resolution. Okay, and so this is ongoing experiments. I think they are writing PRL papers and so on about this. But you can see that here you have the sandwich structure, and with this femtosecond laser, they did transformations here in one of the layers. And if you want to know that it really has transformed, well, you do X-ray crystallography, and you see that this is not a crystal, right? It's silica. And due to this transformation, you can see the patterns here of X-ray crystallography. So you can really induce a transformation of the material at a very, very fine sub-wavelength type of size. Okay, and then the ultimate thing is you try to print the logo of the school you work for, okay? And this is a very, let me just go to the end of it. This is actually using a very sophisticated way to read it. It's not enough to print the Lippmann plate, you have to be able to read it, okay? Otherwise, it's a simple experiment. You just claim that you have beaten the record of storage. So this is third harmonic gain micrography, and you can see this is what was printed, and it is visible, okay? And if you do a cut through the material, you will see that indeed the transformation has happened. So let me finish by talking a little bit about science communication, because you know, on the one hand, that's the closest I ever got to get a Nature paper. So our paper was mentioned in Nature, but didn't make it to Nature. Sorry. And the argument, of course, for Nature to pick it up, if we had proven that the blue sky actually was bluer in the 19th century, I think it would have made the cut. You need this sexiness to make it into Science or Nature. But anyway. I'll come back to the paper, but then we worked again with the museum where we had actually found the plates originally, and we set up a very nice exhibit which is currently running in Lausanne. And if you come to Lausanne, I invite you, I give you a tour of the exhibit, and I think the most interesting picture from the exhibit is this is Jacques Dubochet, who is a Nobel Prize winner for cryo-EM imaging, which is another glitzy imaging method, who visits the exhibit here in Lausanne. And it's a broad public exhibit where we try to explain standing waves and all sorts of things. And I think it's a nice example going from something very esoteric to something that is potentially of interest to broad public. There are a couple of papers about this, and one I want to thank Dave, who was kind enough to shepherd the paper through the various steps it gets to get into PNAS. And the math analysis I just glanced over is actually in a recent IEEE paper. I would like to thank the people who did the work. As you can guess, this is a lot of work in many dimensions, experimental work in particular. Gilles Baechler and Michalina Pacholska, two former PhD students, Arnaud Latty, who is a physicist, and Adam Scholefield and Paolo Prandoni, then the dear sponsors. And with this, I'm done. Thank you very much for your attention.
Good. Thanks, Martin.
Yes, it's very beautiful, this whole technique. And the problem you are asking about the blue sky, of course, is fascinating. Now, you said we don't have the Lippmann plate, but would it be possible to solve it as an inverse problem? That there are some of the things that were on these images that we know exactly the reflection. Is it possible from that to infer what was the composition of the Lippmann plate and then come back on the blue sky, or that's okay?
That's called supervised learning these days, yes, right? So it's a good suggestion, right? Is there a spot that is purely white and we are sure it was a white wall and so on? You need a reference, right, in the end. Yeah. And the problem, that's what we discovered later, is that Lippmann and others who were doing the technique at the time, they were doing a lot of ad hoc methods to make the plates look good, right? So, and that was essentially done by the development process by doing, different mixing of chemicals, different timings or whatever, so they would look good, right? And to them, to look good, they had to compensate for this effect that we did the analysis of, right? And so in some sense, they have done part of the inversion already, but we don't know how much, right? So that's why, unfortunately, it's a great idea, but I'm not sure we can do it. Sorry.
How long was the exposure time to take one of these photos back in the day?
Probably minutes, 10 minutes or so. And when we did them, it was of the same order. So the grad students did a number of new plates.
Not good for sports.
Say again?
Not good for sports.
No, indeed not.
Are there many amateur Lippmann photographers today, or you talk about one?
I would say there was a great specialist here in France, Jean-Jacques Fournier, who I think was the best specialist. He unfortunately passed away. He came to Lausanne actually to look at it. And then there are, like Felipe Alves, probably a dozen people still master this technology. I should say the method is very close to holographic plate recording, right? Because it's interferential, right? And so some people who do holography might also be doing Lippmann photography.
Okay. So Martin, you promise, you made a promise that if someone from this audience comes to Lausanne and to the museum, you're going to personally give them a tour of the exhibition, right? Okay, so this might be a good way for me to get a meeting with you.
As these former graduate students,
Let's take one again.